Okay, so AI search is about problem solving and problem solving related to different types. So we can apply AI search to problems such as robot navigation. In our earlier lectures about agents, we talked about vacuum cleaner agent, and I showed you a video on that also. So you would have actually seen that in that vacuum cleaner agent or robot, the robot actually was moving from one place to another place. Now, how was that decision made? That is like one type of problem. So we call this as a navigation problem. So you can apply search strategies, AI search strategies for problems that relate to navigation, robot navigation. Other category of applications of AI search strategies is games. So you see, when you are playing games, and it doesn't really matter whether it's a single player game or a two-player game or a multiplayer game where there are more than two members or players who are playing that game. So there also in case of game playing, also you have to choose some moves. Okay, so you have done some move and then you have to choose another one, and then you go for another one, and we keep on choosing those moves. Now that choice of moves is primarily done from a number of moves that are available. So you have got a set of moves, and from those particular set of moves, you are actually trying to identify or find out the best appropriate next move. Okay. So that is also a classical example of search. So you have a set of possible moves, and from that set of possible moves, you are trying to identify or trying to find out or trying to play the best possible move. Okay. So again, this falls under the category of AI search. Okay. So I've just given you two very basic examples of search, where search can be applied and where you require some decision in order to select the next action. So that selection of next action is out of a set of actions that are available. Okay, and we'll see a few examples today. I try to develop the motivation of applying this. Okay, so it's not just limited to this. We'll also see maybe of one or two examples that you can apply to even daily life. I mean, if a person is trying to reduce, let's say, is doing exercise and wants to select various exercises, then based upon that, what he wants to or what she wants to achieve, the selection of those exercises is also a search problem. So you have to select them in sequence. Okay, do this first, and then do this, and then do this. So that falls under the category of, maybe you can call, planning. So if you are doing planning, again, there is a search that you'll have to perform. That means that from a set of possible plans, you have to select the best possible plan. And now the question would be that, what do you mean by best? And that's where the discussion becomes more interesting. Okay, so we'll talk about, first of all, we'll talk about what are the various methods or tricks through which you can actually select out of a set of possible actions, the best possible action. So that selection strategy or that selection methods, there is no one method of doing it. There are multiple ways of doing it, and we'll be discussing those ways. And the second thing that we'll be discussing is that how would you compare the two methods? So if someone is performing a problem solving using AI search using method one, and another one of you is using method two, then how would you compare the two? Which one is better? Method one is better or method two is better? Okay. So that is the type of discussion that we'll be having. So you keep these two things in mind, that we'll talk about the methods, which we call strategies also, and then we'll also talk about the comparison, how to compare different methods. And then maybe get some idea that how these methods, or what is probably the best method out of the given possible methods. So there are advantages and disadvantages of methods, different methods of AI search, and we'll discuss those methods also. I hope this is clear so far. So let's move on to the next bit here. So here I'm giving you a very simple example. On the right hand side, you can see that there is a small map. Okay. And this map is primarily showing you maybe a small town, the map of a town, where you have various places. For example, you've got the mayor's house, you have got a bakery here, then you have got someone else farms, then you have got an inn here, a hotel, a dry cleaner, city hall, library. So these are different types of buildings that are present, and then they are connected through some road network. Okay. So here, let's suppose that you are present at the inn or the motel or the hotel here at this location, and you want to find out the best route that would take you to the bakery. Now you can very easily see in this particular representation that there could be multiple ways in which you can actually move from the inn to the bakery. So one route is you go through the mayor's house or by the mayor's house to the bakery. The other possibility is that you actually go via McFain's farm. That is another path that is available. Then, of course, I mean, as a theoretical option, this could also be one of the ways of like moving to the bakery. But you can very clearly see that, okay, there are some paths that are shorter. There are some paths that are longer, and there is one path in which you have got a loop. Okay, so you started from this position. Okay, you took a route via library to the city hall to the dry cleaner, and then you had to come back to the inn. And then, so basically this is actually representing a sort of a loop that you are having. Okay, and then you are actually taking the path from there. So you can actually identify many different paths in this particular case. Okay. So the question would be that what would be the best path? And when I say best path, it would mean different things. Okay, so one can say that, okay, best path could be the quickest path that would take you to the least number of places. Okay, so this, for example, becomes your starting position. We call it your start state. We can represent it with S. This could be your start state. And this could be your end state. And the end state is generally represented by goal. So we can say that, okay, this is your goal. This is your final goal where you want to reach. Okay, and these are the various paths that you can actually follow. Okay, and now let's say if I see this map, perfect, I can actually identify the paths. But if I give this problem to a computer and tell a computer to find me a path, okay, if I ask the computer to find me a path, then the computer has to apply some algorithm, some method to solve this problem. Okay. And what do you think would be the first thing if I ask the computer to solve this problem? Okay. If I program this. So the program is that there is a map, which is a digitized map. Okay. I've got the digital version of that map. I give that digital version of the map to the computer. And now I ask the computer to generate or give me the best path. And I also give the definition of the best path. Let's suppose that I give the definition of the best path. That means that the best path would be the one that has low cost in terms of fuel, maybe, or the best path would be the one that incorporates fewer number of nodes in between. And you can say, when I say node, it means, it could mean that the number of stations in between, right? Which Jihad has just pointed out. So that could be a possibility. So I also give the definition. And then I ask the computer to actually solve this problem. Okay. So what would be the steps involved in this? What do you think would be the steps involved in this? So what would be the first thing that you'll, your method or your approach would do, or you'll actually be presenting this particular sort of a representation inside a computer, then solving it. So what do you think would be the steps? What would be the first step if you want a computer to solve this particular problem?
Maybe identifying the all possible ways to reach the goal.
Okay. And
And
how?
then
Yeah. Go ahead.
then we start comparing them according to the thing we are comparing them upon. Like if we are looking for the quickest path or the low cost path, or the number of nodes. For example, if we are concerned about the number of nodes, we start counting the number of nodes for each path, and the path with the lowest number of nodes will be the best as the thing we are comparing, or yeah.
Okay.
Comparing that.
Yeah. Okay. So you are absolutely right. So the first thing obviously would be that you'll actually be comparing these and comparing different paths. But in order to generate these paths, okay, in order to generate these different paths, the first thing that you'll be requiring is to represent this map in a computer. And that is what we call a representation problem. So the very first thing that you will be requiring is that, okay, this map in this particular form, which I'm showing you in the form of a picture, that will not obviously be understood by a computer. Okay. So in order for a computer to understand that I'm talking about, and I'm actually, my map looks like a particular form, I'll have to convert this into some sort of a representation. Okay. And this is what we call as the representation problem. And you have taken the course of data structures and you have maybe taken the course on programming. There are various ways in which you can represent a problem in a computer. Okay, so for example, representing a map in a computer could be through what type of a representation? So what type of a representation can be used to represent a map? Maybe. Okay.
Maybe a tree or a graph.
Yeah, exactly. So you can use a graph representation. Okay. You can use a graph representation in order to represent this map. Okay, and how would that be done? Okay, so I can actually say that, okay, this is my starting location, this will become my route, and whatever is my starting position, that will become my root node. And then from in, there is a link to Blurry. Then there is a link to cleaner. I'll represent it with C. Then there is a link to library. Okay, I'll represent it with L. Okay, and then from the cleaner, there is a link to the city hall. I can represent it with H here, which is representing the city hall. But because this is a road representation, so you can also go back from the cleaner to your root node, which is primarily your in. So another branch that might get out of this is that from the cleaner, you can also go back to I, which is your start position. I'll represent it with I here. Okay. So similarly, you can expand this particular station, and you can say that, okay, from this station, you can go to the mayor's house. From this station, you can actually go to MF, which is representing the McFain's farm. Or you can also like go back to your start node, which is represented by, or your say root node, which is represented by I in this case. Okay, so this is a sort of a representation that you can very easily use for representing a map of this sort. Okay. Now you know the difference between the graph and a tree. If it is bidirectional, then, or if there are loops there, if it is bidirectional, then primarily we'll actually be representing it as a graph, or we'll call it a graph. If it is a unidirectional, then primarily this would be a tree representation. Okay, tree representation, or solving or representing a tree or applying search strategies on trees is relatively easier compared to applying search strategies on graph. But generally, maps are represented by graphs, because you can move from one place and then you to another, and then you can actually come back to the same place. Okay, so here, okay, so all these links are unidirectional, but there are loops in it. So you can move from I to B, and then you can move back to I. So this is how you can actually represent the loop. And what would happen after I here? After I here, this whole thing, which is under I, that will get repeated. Okay, so you will get a repeat of this. And that is generally not represented. And that would tell you that, okay, this graph or this tree representation could expand infinitely long, because there are lots of loops that are there. Okay, so the size of this would be enormous. Okay, so that's actually the problem with this. So one way of solving this problem would be to avoid loops, and we'll come to that point later on. Okay, so that's like the first problem that we have when we are solving things using computers, which is to represent a problem. Okay, and this is what we call as a representation problem. Okay, So if you have got a representation problem solved, then you can move on to the next part. Okay, and the next part here is primarily how to actually use this representation to solve your problem of finding the path between. Okay.
Why did we choose it to be a unidirectional graph?
Okay. So, I mean, that's just a method of representing. You can actually have it bidirectional also. That would represent a concise representation. But then it's up to you. I mean, you can have a bidirectional representation or you can have a unidirectional representation. That's a mere, what you can say is actually your choice. So we can also represent them as bidirectional connections. For example, I here connects to, let's say, C, and I'll say that, okay, this is bidirectional connection. So that's like one way of representing it. The other way of representing it is that I represent it in the form of a tree. And I say that, okay, from I, you can go to C, and then from C, you can actually go back to I. That's one and the same thing. Okay. But then if you are using this bidirectional, unidirectional representation, then you can apply algorithms, tree algorithms on this, right? So just it's your choice, basically. Okay, so it's nothing that is compulsory that you actually have to represent it in this particular form. It's not really necessary. You can represent it as a bidirectional connection also. No issues. Okay. So it looks a bit more easier to understand in this particular format, but the other thing is also like the same thing. You can have bidirectional or you can have unidirectional connections. Okay. So I hope this is clear. I mean, there is no as such any rule here that you have to have a unidirectional or one directional connection. You can have bidirectional or a graph representation. It's the same thing, but it's more easier to traverse a tree, right? It's more easier to actually traverse a tree. Representation is much clearer. Okay, so that's why you use this representation. There is no other reason for doing it. I hope, Rania, this is clear.
Yeah, it's clear. Thank you.
Okay. Okay, so let's move on to the next slide here. And okay. Okay, so the problem solving part, the first thing that is required in problem solving is, as I told you, is the representation. And we have discussed that representation. You can actually represent it in the form of a tree or a graph, whatever formats you think is appropriate. And that's what the representation problem is. So we have solved one bit. And that's where your knowledge of data structures and your knowledge of programming comes in. Okay. And this is where it actually links together. The first of all, you have to have a representation. Okay, the next, and this is an example of the same thing. We have got a maze here. And it's a maze that we want a computer to solve. And right on the left-hand side, we have got the maze representation, a standard maze. So you can, this is your start location, right? And this is your finish location. You enter the maze from this side. Okay. And then you exit the maze from this side. Okay. And you need to find out a path that connects your start location and your finish location. And again, the first thing will be to represent it. And in case of representation, you can actually label some points on this maze as they have been labeled on this slide, A, B, C, and D. Okay, so how would you label them? Okay, why didn't I say, why did I put A here? Okay. Why not, let's say, and then I put a B here. Okay. So where to put these nodes or these numbers or these states? We'll call them states or nodes. Where will you put them? Okay. Would there be a rule behind this? And of course, when you are solving a problem, you have to devise this mechanism. You have to come up with this mechanism of defining where to put these nodes and then how would you represent them. Okay. So what do you think where these numbers would come, alphabets would come?
I guess we have to identify them so they using them we can and identify the all possible ways from the start to the finish points.
Okay. So one way of identifying where to put these alphabets, A, B, C, and D, is that wherever you have got a junction, wherever you have got a point where there are two different parts of the maze connect with each other. Okay. Or wherever there is a change of direction. Okay. So for example, if you look at A, you are coming from this side and there is a change in direction here. Okay. So therefore, wherever there is a change in direction, you put a number there or an alphabet there, and that is representing A. Okay. Then similarly, B, at B, you have a change of direction. You have possible direction. You can either move in this direction or you can move in this direction. Okay. And that's why we have put an alphabet here. Now we could have actually put an alphabet at this place, which is missing in this case, but you'll have to put it here because if you want to move in this direction, then you'll have to have a node or a state at this particular point in, location. So the first thing that you will actually be doing is that you will be identifying all the junctions, all the points where there is a change in direction or where there is a possible choice of taking actions. Okay. And then, of course, you can put an alphabet there that would represent a node. Okay. And then obviously, if I represent it in the form of a graph, you can very easily do that, connect all these together. Okay. And how will you connect all these together? Let's just see. If I just erase this for a while. Okay. So I can actually say that, okay. So what would be a graph or a tree representation here? So from start, we come to A. From A, you go to B. And then let's say that we put an F here. So you can also like say that, okay, from A, you can go to F. And then from F, you can go to B. From B, you can go to C. And then from C, you can also like put a alphabet here. And then from that, so these could be like different types of nodes which you can actually represent. Okay, and of course, A is not directly connected to D. If you want to go from A to D, you have to go via F, B, C, and D. Okay, and that would be one branch of your tree. Okay. And then similarly, if you want to go to E, this is the path that you'll actually be following from A, F, B, C, and E. And that would be another branch of the tree. But up to C, it's common. Okay. So similarly, this is just a small part of the representation, but you'll have to do it for the complete maze and then represent it in the form of a tree or a graph, right? And because you can move back from A to from A to the start position. So these connections would be bidirectional. So you can, like, if you want to represent it as the graph, under A, you can put another child node as start. Okay, so if you want, you can actually do that for completeness, or you can have all these connections represented as bidirectional connections, so you can move back and forth coming from one uh, point to another point and then move back. Okay, right. Right. So this is primarily the representation part. And let me just see if we can like look at some other examples here, and maybe and see that how this. So this is primarily the very first thing that you'll actually be doing, representing your problem, and then comes the next part, which is primarily solving this problem, and that is where we'll actually be talking about that. So this is again another representation of a navigation problem. This is primarily maybe a map that is a maze in which we have got all these numbers from 0 to 20, and they are connected through these dotted lines. And these are primarily representing what you call as a graph representation. You can draw it as a graph very easily without any issue or without any problem. So that's primarily the representation part. Okay. And okay, so every number here is representing a junction or a turning point, which we have already discussed. They are all connected. These points are connected. And then the task here is to find the path from 0 to 20. And so that's again our task, which we have defined. Okay, and then there could be various methods that can actually be used. Okay, so we'll come to this the solution part in a while. Okay, and that solution part would be that how can you actually find this path, and that's where these different algorithms will come in. Okay, so we'll talk about these algorithms in a while. So you start from 0, and then the goal point is 20. That's again a robot navigation problem. So the question here would be the choice is to turn left or to turn right, or to move straight. So these are the questions that needs to be represented. Again, another example of maze representation. You can see that, okay, you have got this representation of a maze, and then you have got a graph representation of the same. Okay, another representation, which is showing you again different nodes that are connected together. And then once we are done with this representation part, then we'll move on to the solution part. Okay, so let's see how would let's say let's before we move on to the solution part, so let's just say that, okay, you have got this representation here, you have got this sort of a maze, and you start from a particular location and you want to go to the end part. So the first thing would be that you should think of how a human would solve it. Okay, how would a human solve it? Okay, so it's not that difficult to understand. So I can give you a basic idea of this, that, okay, if you start from your start location, and then of course if you are at this junction, okay, then the choice would be that you move in this direction, okay, which is towards your right, or in this direction, which is towards your left. And then if you choose to move towards the left, then there is a choice that you can again move in this direction, or you can move in this direction. Okay, so how would a human solve it? Now there could be two situations. in this particular case. Okay. One is in which a person is clueless. I mean, doesn't have any idea where the end point is. Have no idea about where the end point is. So of course you start from your start location, but you don't have any idea that okay, where would the end point be? So the person is what we call as clueless, no clue about the direction of your exit point. Okay, and in that case, what you will do is that you will explore everything. Okay, so if you are here, you will actually be you will not leave this left part. You will go to the left part or to the right part. Suppose you choose the left action. So you say that okay, from here you will turn left. From this point you will turn left, and that is just a choice that you have made. Okay, and because you are clueless, you don't have any idea you have to move to the right or to the left. So you said that okay, let me just try the left side first, and you will actually go all the way here, and then you will again from here you will actually say that okay, if I reach this point here again, I'll move to the left. Okay, so the person has actually made a set of a small rule here, and that rule is that whenever I reach a junction, whenever I reach a point where I have a choice of moving left or right, I'll always move. I'll always move to left. Okay. Now that's a self-made rule. Nobody have actually told you to make that rule, but you have actually said that because you don't have any clue, therefore you said you said that okay, you'll always take the left turn, or the left turn will be preferred over the right turn. And of course, if you are here, you will take this left turn. If you are here, you will take this left turn. If you are at this point, okay, if you are at this point, again, you will take the left turn, okay. And if you are at this point, you will again take the left turn and you will continue. And ultimately what will happen is that you will end up at a space where there is no exit. Okay. And then what will happen is that you will go all the way back to this point and then go for the right or go for the straight. And that would be the matter of choice, the matter of preference. So the example which I've just given you is where you have given a preference to left turn over moving straight and moving to the right. So you will say that, okay, if I've got a choice of moving to the left, I'll always take the left turn. If I've no, let's say option left, then I'll prefer moving straight or moving right. Now that is a sort of a rule that you have developed. Okay, if you are to explore this. Okay, so you say that, okay, you will start from one corner and you will always take the left turn. And you could have actually, let's say, decided the other way. You could have actually said that, okay, wherever there is a junction, you will prefer the right turn. Okay, and if that happens, then of course, if you were here, you would have taken this path. Okay. And if you were here, you would have taken this turn. Okay. Now you can very easily see in this particular setting that you have said to yourself that, okay, you will always prefer the right turn. And again, if I prefer the right turn, you will end up at a place which is far away from your exit. Okay. Why you have done this? Because you are clueless. You don't have any clue about your exit, where your exit is. So you have to actually explore. And when you are exploring it to make it systematic, you will actually be saying that, okay, I'll always take the left turn, and when there is a tie, I'll I'll obviously prefer the left turn. If I'm not left with an option of moving, or if I end up at a place where no other option is left, then I'll rethink and then I'll take the right turn. Or you could have actually suggested to yourself that, okay, you will prefer the right turn. So if you prefer the right turn, then of course this would be the paths that you will actually would have followed. If you would have preferred the left turn, then this would have been the path. And this is a sort of rule that you have developed on your own. Okay, nobody have actually told you about that. You have developed that rule on your own. Okay, and you follow that. Okay. And it's this rule that is actually where the problem solving comes in. That what type of a rule or what type of a method or what type of a strategy you develop to solve this problem. Okay. So the first thing in problem solving using AI, the first thing is the representation thing. You have to represent the problem. The second thing is that you have to come up with a strategy or a method to solve it. Okay. Let me just see if we can move further. I hope this is clear. Are there any questions about this so far? Is this thing clear?
Yes, it's clear.
Okay, great. So that is in the case when you don't have any clue where your exit is, okay, or where your endpoint is. But now, let's say that you have got some domain knowledge. When we say domain knowledge, that means that you have some idea where your exit could be. Okay. So let's just maybe if I move forward, that might help you. Okay. So what if you have got some domain knowledge? And what do we mean by domain knowledge? By domain knowledge, we mean that someone, maybe you talked to someone before entering into this maze, and someone told you about the possible location of the exit. Okay. Maybe your friend or someone said that, okay, if you see this, then from this particular point, or if you get to your first junction, which is here, someone told you that, okay, don't go to the left side because you will end up going into a dead end. Okay, so you should always prefer the right turn. Maybe someone told you before entering this particular maze. Okay. And now that knowledge that you have got from someone else is what we call as the domain knowledge. Okay, so you have got some clue about that. So you are not completely clueless. You have got some clue here. And you can very easily see that because of this clue, your search space has actually reduced. Now you'll only be searching in this part of the for your exit of the maze. And this part, the lower part, because of this clue, has actually been eliminated. So your search has reduced. And why has the search reduced? Because of that domain knowledge, because of that clue that your friend who might have gone through this maze earlier have given you some hint. Okay, so that's like one example of domain knowledge. And the second example of the domain knowledge exactly could be that. So let's suppose it's a day, and you are getting some light that is coming out of this or coming in from this exit, from this end. Okay. So what you will do in that particular case, if someone tells you that, okay, or I mean, you yourself actually know that, okay, your exit is in the direction from where you are getting some light. Okay, so you enter your maze and then you start looking for a direction in which the light is coming from. So suppose your friend told you that, okay, you should always go to the right when you reach your first junction. And then you have also got this clue that, okay, there is light that is coming from the exit side and the other side would be dark. So there would be some light coming from this side. So if you are at this point, you will turn left and you will turn right and you will see that, okay, from where or from which side you are getting that light. And that might direct your search, okay, towards this direction. So because of this domain knowledge that you have got, because of this common knowledge that you have got about problem solving, your search has further reduced because you have got some more information about your goal, about your exit point, right? And that's what you call as domain knowledge. So there was an initial example in which you were clueless. And there is this second example in which you have some clue about your goal, right? So in both cases, you can see the difference. You can see the difference in both cases very easily. In the first case, when you were clueless, you developed your own route. If you were very, very lucky, you would have actually gone towards your exit. Otherwise, you would have to explore the complete maze. Okay. And you might have to come back to your starting position, go to another direction, then come back, go to another direction, then come back. And that is a sort of an hit and trial sort of a method, right? Where you are clueless. But in second case, when you have got some domain knowledge, there you are not clueless. There you have some clues. And if the number of clues that you are getting or the number of ideas about your end or your exit point, if you are getting more and more information, your search becomes smaller, okay, or becomes more efficient. You require less time. Okay, so I gave you just two examples. One was that you got this knowledge that, okay, from your first junction, you should turn right. That is something that you got from your friend. And then you got another clue that then you just follow the light. Okay. And if the light is coming from a particular direction, you just follow that. And you can very easily see that if you follow this particular route or if you follow these particular clues, you can very easily reach this. And that is probably the best path that you'll actually be getting. Right? Is there any question about this? Okay, that's wonderful. That's excellent. Okay, so the discussion which I've just had actually gives us the method or the strategy to solve our search problem once it's being represented. Okay. And that is the point that we'll actually be discussing probably in the next few points. So domain knowledge, I've given you this clue that, okay, if you've got domain knowledge, that would help. And that would definitely assist you in in getting towards your exit, right? Okay. So this is again an example of representation. So now this is primarily the representation of your the same maze which I've shown you earlier. So if you start from here, in the first case, when you were clueless, so your destination is 9 in this particular case. Okay, so that's your destination, which is 9. Your starting point is 1. So that's my start state. That's my goal state. And let's say you said that, okay, you will prefer the left side in this case. You are at 1. So what would be the strategy of solving this? I mean, now you give me an algorithm to solve this in case you are clueless. So what would be the problem solving strategy? Okay, if you are at 1, what is the first thing that you will be checking at this point, at this node? Now remember, now the computer is actually solving this. You have implemented this inside a computer and you haven't given the computer any clue. So it's a clueless situation. Okay, you have not given any domain knowledge. You want to move from S to G. Okay, and as rightly pointed out in one of the by, I guess it was, yeah, Dina, that you can apply depth first search and breadth first search. How many of you are familiar with this? I hope all of you have read these search strategies. Okay, on a tree. Okay. So
I think few students knew this algorithms.
okay. So I'll just then explain this. So let's say you are clueless. So what will you do? What will be the search? What would be the algorithm? What would be the method of solving it? Okay, so the first thing that you'll actually be doing is, if you are at a particular point, wherever you are, you'll have to perform a check. And what would be that check? So let's suppose you are at 1. What would be the check that you will be performing at 1? What would be the test? Okay, let me call it a test. So you perform a test here. What do you think should that test be?
Whether to go to 4 or 3 or 2.
Okay, now even before that decision, whether to go to 2 or to 3 or to 4, there is another test that you'll have to perform. Remember, this is an algorithm, or this is a solution strategy that you are developing for a computer to solve. Okay. So the first thing there should be the very first test that you'll have to perform at every node. Whenever you go to from one place to another place, from 1 to 2, at your current location, you'll have to perform a test or a check. And that will be done through a function. You will write a function for it. Okay, you will program a function, or you write a function for it. What would be that test? Yeah. Anyone?
Where we are totally clueless.
Okay. Any wild guess? Any guess? Remember, what is your goal? What is your ultimate aim? Your ultimate aim is to go to which node? 9. Right? That's your ultimate aim. So what if, now let's just think about it. What if you are already at 9? Will you still try to go to any other node? Of course not. Okay. And how would a computer know? How would an algorithm know whether you are at 9 or not? you'll have to perform this test first. Okay. Okay. And that, okay. And that would be, you will check at every node whenever you will go to a new node, whenever you are at your current node. Okay. You'll always perform a test, and that would be a check. And that check would be whether this node is your goal node or not. Is this 9 or not? Okay. That test will be done every time. Okay. So if you are at 1, if you are at a particular node, you will check. Your first check would be that whether you are at your goal or not. Okay. So you will yeah. So that is the first test that you'll actually have to perform at every node. Okay, so if you are at 1, the very first thing that you'll actually be doing is that, is this node where you are at present, is this your goal node or not? And the answer, of course, in this particular case, when you are at 1, the answer will be no. This is not your goal node, right? Your goal node is 9. So this is not 9. Right? Okay. Then comes the next step. Then you decide that if the answer is no, then you decide and try to find out whether you will have, from 1, you will go to 2, to 3, or to 4. That comes at the next step. Okay, so the first step is always to check whether the present node is your goal node or not. And the next would be, if the answer to the first is no, then your decision will be that, okay, decide your next node. Which one will be your next node? Okay. So if you are totally clueless, if you don't have any idea in which direction is 9, okay, so then let's say we apply the same strategy, and that strategy is that, okay, I'll prefer the left node. The preference is the left node. Okay, I'll always prefer the left node. Okay, so from S, we'll go to this node. Okay, and when we'll reach this node, which is the left, on the left branch, we'll again perform that test. Of course, this is not your goal node. Then what will you do? You will again go to the left branch of 2. The left branch of 2 is 5. Okay. And you will again basically reach a point where you get to 5. And of course, 5 is not your goal node. Therefore, you have actually got stuck at 5. That means that, okay, there is no left, there is no further left branch of 5. So you will stop at this point. And from here, what you will actually do is that, okay, you will say that now if the rule is that you will always prefer the left branch, and if the left branch is not further expanding,
We
then
check the
yeah, please go ahead.
If the left branch is finishing point, or it doesn't have a left branch,
Leaf node,
so go and check the right one.
the right branch. Okay, and that's the rule which we have set. Okay, so now what we'll do is that from 5, we'll go back to 2 and check the right branch. Okay, and the right branch is 6. Again, perform that test, the check. 6 is not your goal node. And then you go all the way back from 6 to 2 to the parent node of 2, which is 1. Okay, and then you go and check 3. Okay, the central one. Okay, and this is the leaf node. Of course, the test would fail here. You will try to expand it. There is nothing to expand because that's a leaf node. Then you go to the right branch. Okay, and then you go to 4, and again the rule here would be that the left branch would be preferred. So from here you will not go to 8, you will actually go to 7. Check this. This is not your goal node. Expand it further means again move to the left node, and now you will reach 9, and 9 is primarily your goal node. Your test will pass in this particular case. Okay, and this primarily will give you the paths. So this primarily will give you the paths. Okay. Now, remember, this was the situation when we were doing it, when we were clueless. Okay, and this was actually done in the planning stage. We were actually planning to solve this maze. Okay. So, okay. So this is like one strategy when you are actually clueless. Okay. So that's like one strategy. Okay. So we call this strategy as depth first strategy. Okay. So, and this is called depth first strategy. Why do we call it the depth first strategy? Because you take one branch and then you keep on exploring the left nodes of all on that branch till you reach the final node on that branch. So you started from 1, you went to 2, then expanded the left branch, you went to 5 and you can't expand it further. Then you actually backtracked and changed direction. You started exploring the other one, okay, which was 6. You came back again here, you started exploring the middle node, it can't be expanded. Then you went to the right node, which is 4, and then you started exploring the branch, which is on the left hand side. So you went from one node here, okay, and you went to the other one, and then you went to the other one, and they were all on one side. They were on the left hand side of a particular node, or the right hand side of a particular node. So you take one branch, one complete branch, explore it completely till you reach the last node, and then you change direction. That's why we call it depth. It's depth. So you call it depth first. So this is what depth first would be. Okay. And that's the situation when this is when you apply when you are clueless. Okay. So you select one branch, explore it till the dead end, and then change direction. Right? Okay. So that's like one possibility. I hope this is clear. Right? So is this discussion clear? Okay. I hope it is also clear to those who haven't studied depth first and breadth first before, to all of them, right? Okay. Now let's just talk about another strategy in the same scenario. Okay. And that strategy would be that, okay, let me just rub this first. Okay. And that strategy is, okay, that strategy would mean that, okay, here I'll not go, I'll not set a direction. I'll not say that, okay, I'll prefer the left over right, and I'll only explore the left branch till we go to the last node. Here, what you say is that you say that, okay, I'll start from the left side and I'll just go one step towards the left side. And then if I don't get the goal, then I'll change the direction immediately. Okay. So the example in case of a maze would be that, okay, if I start from 1, I reach this point here. In the earlier case, we said that, okay, we'll go to the left and then keep on exploring the left side. Here, what we'll be doing is that, okay, we'll say that, okay, we'll go to the left, but we'll only go one step towards the left. And if we reach the goal, fine. If we didn't get the goal, then I'll immediately change the direction and go to the other branch in the hope for finding the goal. And if I don't get the goal here, I'll again change the direction. This is one step. So at every step, I'm changing direction. So this is primarily from here. What we are doing is that if we are here, we'll say that, okay, I'll go one step towards the left. If I find the goal, fine. If I don't find the goal, I'll come back and go straight. Okay, one step to the next junction. If I find the goal, fine. If I don't find the goal, I'll come back to the junction and then go the other direction, which is 4. If I find the goal, fine. If I don't find it, then I'll basically start following or expanding the first branch again. So then I'll go further from 2 to the next level. Okay. And if I find the goal at this level, fine. If I don't find, then I'll stop at this point and expand the other way. If I don't find the goal, I'll expand this way. Okay? And this is what we mean. This is what it means, that we move from, we explore all the nodes at a particular level first before moving on to the next. Okay. So coming to this graph, what we'll do is that from 1, we'll actually check for 2. We'll not expand 2, we'll not further expand 2. If it is not the goal, we'll expand 3. If 3 is not the goal, we'll expand 4. Right? If 4 is not the goal, then what we'll do is that we'll expand 2 further. Right? So we'll evaluate 5. Then we'll evaluate 6 because 6 is also at the same level. 3 cannot be expanded further, so we'll not expand that. 4 can be expanded further, so we'll go to 7, expand it. And then we'll go to 8, expand it, cannot be expanded further because there is no child here. And then this way we'll actually continue. 5 and 6 cannot be further expanded. So from 7, you'll actually expand to 9. As soon as you reach the 9, because remember, whenever you will be going to a new node, you will be doing a test. So at all these nodes, you will be performing that test, whether this is your goal node or not. And finally, when you will reach this, your search will stop. Okay. So what is happening here? It's saying that before you go to the, before you move from one node to another node, you actually explore all the nodes at that level. So this is level 0. We call it level 0. This is level 1. So before moving on to level 2, which are the children of level 1 nodes, you will explore all the nodes at this level. So that is another way of saying it, that if you are at a junction, you will go always one step in each direction in a hope to get a node, in a hope to get to the node, goal node, right? So that means that you will explore 2, you will explore 3, you will explore 4. If you don't get the node, then you go to 2 steps further. Okay, so from 2, you will go to this particular node. From 3, you will go to its child. From 4, you will go to its child, which is 5 and 6 of 2. 3 doesn't expand further. 4, you have got 7 and 8. So you will then explore 5, 6, 7, and 8, which is at level 2. So all these nodes will be explored before moving on to the next level, which is, let's say, level 3. Okay. And that means that your search is actually expanding in all directions at the same time. Right? So you choose not just one direction. In fact, you go one step in all directions. And this is covering the breadth of your search. And we call this as breadth first search. Right? So here there is the preference of the first node, that okay, out of 2, 3, and 4, will you expand 2 first or 4 first or 3 first? That's the choice. Or will you go to 2, 3, or 4 first? That's the choice only. But then you will explore, or you will actually evaluate all these nodes before moving on to the next level. Okay, so in other way, all nodes that are directly connected, they will be explored first before moving on to the next. Right? So you can see here that 1 is directly connected to 2, 3, and 4. So 2, 3, and 4, all these 3 will be evaluated first. When we say evaluated, that means tested for goal. Now, after that, 2 and 4. So 2 is directly connected to 5 and 6. 4 is directly connected to 7 and 8. So 5 and 6 are directly connected in this particular case. 7 and 8 are connected. So you will explore 5, 6, and then 7 and 8. Okay. So I hope this is clear. This is what we call as breadth. Breadth first. Okay, breadth. So is this clear, Ji? Is there any question about this? Yeah. How is this happening? Okay, wonderful. If you want, we can have a break of maybe 5 minutes before we start. So we can have a break of, let's say, 5 minutes, and then we'll start. So we were discussing this problem earlier, and we said that, okay, if you are clueless, if you don't have any clue, if you don't have domain knowledge, then primarily there are 2 ways in which you can actually resolve this problem, and that is either you go depth-wise or you go breadth-wise. When we say that you go depth-wise, it means that you take one branch and you explore all the children of that branch before changing any direction. So that means that if you start from 1, you go to this point, then you prefer, let's say, 2. From there, you explore the children of 2. Okay. And then once you have explored all the branches under 2 and all the nodes under 2, only then you change the direction. If that is the case, then we call this as depth first. The other strategy is that you can actually go step by step. That means that you explore all the nodes at a particular level. So that means that after 1 is directly connected to 2, 3, and 4. And you explore 2, 3, and 4 first before moving on to their children. Right? So we explore 2, then 3, then 4, and then we go to the children of 2. We'll explore the children of 2. There isn't any child of 3. We'll not expand it further. For 4, we'll explore 4 and 7. And this way you actually move on. So that means that you actually have level by level exploration, which is called depth first. So you start from this, then you explore all the nodes at this level. Then you explore all the nodes at this level before moving on to the next level. Okay. So this is when the situation is such that you are clueless. Now, so this is what breadth first and depth first strategies are. But remember, you apply these strategies when you don't have any domain knowledge. If you have got domain knowledge, that means that you have got some clue about the direction of your goal, in that case, you don't apply these solution strategies. You try to actually select a node. Let's say at this level, the choice is between 2, 3, and 4. If you have domain knowledge, then the domain knowledge should be good enough that you should straight away select 4 instead of 2 and 3. So your search should be directed towards 4. Why towards 4? Because 4 is connected to your goal. Okay. So if your search is goal directed, that means that you have got some domain knowledge. Then there are other search strategies that you apply. And one of the common search strategies that you apply is what you call as A star. Okay, A star search strategy. We'll talk about A star later on, that how this actually goes and how the domain knowledge is incorporated in this type of search strategy. We'll discuss them at a later stage. Okay, let's move on. So if you are solving a problem using a computer, you are trying to develop an agent which is searching a maze, or if it is a robot agent which is navigating a certain place, then in that case, the first thing that you'll have to do is you'll have to represent the problem. The second thing would be that you'll have to apply the search strategy on that. And finally, you'll have to write down a program for it, okay, or implement it using Python or any other language. Okay, right. So just to summarize, you may have domain knowledge about your search. You may not have domain knowledge. If you have domain knowledge, then the challenge would be how to incorporate that domain knowledge in your search. That is primarily one of the challenge. Okay, how to incorporate your domain knowledge in your search. That means that if you remember in a previous example, what would be that domain knowledge? Say, for example, if you have some domain knowledge, how would you incorporate it into your program, into your computer program? That is the challenge. Okay, and this is where A star algorithms and there are a few other algorithms that are used to incorporate your domain knowledge into your search. Okay. Okay. So in summary, if your search is with domain knowledge, that means that your search incorporates domain knowledge, then this type of a search or this type of a program will be called an informed search program or an informed agent. We call it informed agent. Okay. Or at times we also call it heuristic search. Okay. Heuristic search. We also call it heuristic. So these are the two terms that are interchangeably used: heuristic search or informed search. So either you call it heuristic search or informed search. Remember, heuristic or informed search is a search that incorporates your domain knowledge in your search. That means that your search becomes more and more efficient. Okay. And the second one is, of course, the search which is without domain knowledge. We call this as blind search or uninformed search strategies, okay, or blind search strategies. So breadth first and depth first, which we have just seen in the previous example, both of these search strategies fall under the category of which search? With domain knowledge or without domain knowledge? Will we call them informed searches or blind searches? Yes. Anyone? Yeah, so shall I repeat the question? Okay, so the question is that earlier we talked about these search strategies in this example. Okay, so we said that okay, you can apply depth wise or breadth wise. Okay, so my question is that these two search strategies, will they fall in the category of informed searches or blind searches?
Blind search.
Blind search. And the reason for that is,
Because we don't know or we don't have a domain knowledge where our goal is located.
okay, so you don't have the domain knowledge, therefore you search blindly. That means that in one case you move from one level to another level, and in the other case you just select a branch and you go all the way in search of your goal without having any clue about your goal. Okay? And so they'll fall under blind search strategies. And we'll discuss with concrete examples the differences between the two. And the interesting part in our discussion will be where the real AI part comes in, is how to incorporate this domain knowledge into your search. That's where intelligence comes in. Okay. Okay. So, right. So the next step obviously would be that what are these strategies? We'll discuss these strategies in detail and how these strategies are implemented. But before that, here is a small challenge question. I'd like you to spend a couple of minutes on this. The question here is that here is a representation of say some exercises that you can perform on certain machines. The number on the link which is given, that suggests the time it takes to burn 300 calories. Okay. And the goal is that we want to find out a sequence out of this sequence of various training exercises. These are body exercises, such that we get the maximum calories burned in the least amount of time. That's the challenge, right? Of course, we can try to solve it now, but maybe when I'll share these slides with you, you can try to look at this and try to find out, using the strategies that we have discussed so far, whether you can solve this problem or not. Or you can come up with your own strategy to solve this type of a problem. Okay. So we want to come up with the shortest possible time that burns the maximum possible calories. Okay. So again, what we have done is that we have taken these various exercises, we have connected them through a representation, which is a tree representation in this particular case, with the numbers given on each of these branches, right? Now, you can see the selection in our case, now the selection would be biased towards the time. Okay, so you will actually be looking for an exercise that takes less time, right? So now it's not completely blind. There is some knowledge about domain that is given here, and that is about time. Okay, so this 10 here, this 16 here is primarily giving you. So what is this 10? 10 is the warm-up time. 16 is the step mill time. If you perform this exercise on this machine, in 16 minutes, you will burn 300 calories, right? So similarly, there is this pulling bar, there is this machine here. If you work on this machine for 6 minutes, you will burn 600 calories. Okay, so there is some domain knowledge that is given here. Okay, I'll leave this for you to look at it in your time and try to come up with a solution with this. Okay, so this is just a small question for you. Okay, so here is another question which we'll try to resolve now. And that is that how to reach from your start goal to your goal node in the presence of these obstacles. It's a robot navigation problem. And your algorithm should be such that you also have to avoid these obstacles. So this is an obstacle here. Here you have got the obstacle. You have to find a path. Okay, that connects your goal. Yeah, of course, you can put a boundary around it. I didn't show the boundary. You can put a boundary here. Okay, so this could be the boundary, right? So, and then, of course, what would be the strategy here? How would you solve it? What would be the first thing that you'll be doing? What would be the second thing that you'll be doing? Okay, and if you don't have any domain knowledge, what will happen? If you do have some domain knowledge, how would your search proceed? Okay. So what would be the first thing? Representation. How would you represent this in a computer? This problem?
We can also put some labels as we did before.
Okay. So what would be the way to do that? What would be the easiest way to do that?
We can put, for example, a label called A in the left
Mhm.
corner, and
Maybe here
a little bit for
towards the obstacle. Maybe
Yeah.
here.
yes,
Yeah. Okay.
and a label called B at the right one.
Okay.
And then we go put C on the
Maybe
center.
maybe
At
here.
the top. Yes.
Maybe at this point. Okay. Okay. So we can. You're right. I mean, your approach is absolutely right. But an easier way of doing that would be that on this, what you can actually do is that you can superimpose a grid. Okay, it's just like a grid that you have imposed on this particular representation. And now it becomes really easy to label. Okay, so I can actually say that this is S, this is my start node, this is A, this is B, this is C, this is D, this is E. Okay, and similarly, all the cells that I have got, I can label these cells. Similarly, I can say that, okay, this is F. I can start from one end and I can keep on labeling these. Okay. So rather than doing it the way that we were doing earlier, an easy way would be that you have this scenario, you superimpose on this a grid. Okay, and you can actually say, you can define the size of the grid. Okay, let's say the complete arena here, or the complete size of this particular domain is, let's say, 100 meters by 100 meters. So you have got, let's say here, I'm just giving you numbers. So this complete distance is 100 meters on this direction. Okay, and then you have 100 meters on this direction. Okay, I mean, these are just numbers, for example. Okay, and then you can put a cell here, and that cell would primarily would be of some size. you can say that, okay, this could be, let's say, divided 1, 2, 3, 4, 5, 6. There are 6 cells, so 100 divided by 6, that would give you the dimension of this cell. Okay, right? So this would be similarly, you can actually say the size of this cell. So you have actually imposed a grid. And now, once you have got this grid on this, now labeling becomes very easy. Okay, so how to avoid obstacles? Of course, you will not put any, you will not label this cell here. You will not put it in your graph or in your tree, because you can't really go to this particular cell because there is an obstacle here. This will not be included in your graph or a tree. This will not be included in your graph or a tree. Okay. You may exclude them. You may exclude this cell. You may exclude this cell. All these cells will be excluded, right? Okay, and you can label all the other cells. And now let's apply breadth first here. Okay, so let's apply breadth first or depth first in this particular case. So let me just rewrite this. So let's say this is A, this is B, this is C, let's say this is X, this is P, this is D. I can label these numbers. I can label this as E, and I can label this as F. So if it is depth first, what would, and if I prefer the left node, okay, how would my search proceed? Let's say. So from S, if it is depth wise, from S, I'll go to
A.
You will go to A. And from A, you will go to the child of A, which is B. From B, you will go to the child of B, which is
C.
C, right? From C, you will go to E. Okay, and assuming that you can't move diagonally. I mean, of course, if you can move diagonally, then B and D would also be connected. Assuming that you can only move straight, left, or right, diagonal movement is not allowed. In that case, you will actually go to this node, and then you will go to this node, and then you have a child of this node, and then probably you will go to this. So this is how your depth wise your search will progress, right? And if I apply breadth first search in this case, let me apply it with some other. So in that case, firstly, you will explore A, then you will explore X, then the child of A, then the child of X, then the child of B, and then the child of P. And this is how this would explore, right? Clear? Yeah, so is this thing clear? So you can very easily see that I have automatically avoided these obstacles because I'm not including those cells in my search where the obstacle is. Okay. That's of course a static way of, or I can avoid obstacles which are not moving. If the obstacle is moving, the situation becomes a little difficult. Then that's a different story. Okay, so now let's just say that you got some domain knowledge, and I tell you that, okay, what that domain knowledge is. Someone tells you that, okay, your goal is in this direction. Okay, so if this direction is known, right? So if someone tells you that, okay, so now you have got some domain knowledge about the goal. Okay, so then Of course, if you know that your goal is in this direction, moving in these directions will become fruitless. I mean, you should avoid moving in these directions. Okay? Moving in this direction may be or moving in a direction which is taking you away from your goal. For example, moving in this direction, keep on moving in this direction may not make any sense, because this may be in taking you away from your goal, right? So if someone told you that, okay, your goal is in this direction, then in that case, the search strategy will become relatively more easier. Okay, so if you are here, let's say, of course, you will have to take the first step. You will go to this cell. Okay, and then from here, you don't have any choice. Obviously, you will go to this cell. From here, you don't have any choice. You can actually move to this cell. But now you have got a choice. The choice is either you move to this cell or you go to this cell. So that's the choice. So either you go this way or you go this way. So what will be your choice? Let me call this as the cell F. Let me call this as F, and let me just call this as E. So now it's your choice.
If because it's towards the
Exactly.
domain data we have.
Exactly. And you will actually move towards F. The reason for that is that this would actually take you closer to that direction in which the goal is. Of course. And now from here, you have a choice of moving in this direction and moving in this direction. Well, of course, again, the choice is easier,
Going
quite
to the
going up, right? Or going towards this particular cell. Let's call this as X. So moving towards X would be my choice compared to Y. Okay. So if I incorporate this domain knowledge into my search, then my domain knowledge should direct me towards my goal. This is what the difference is. Okay. And from X, I can't really move back to E. There is a possibility I'll not go there, because that's taking me away from this line. I don't have any other choice other than moving to this particular cell. Okay. And then the choice is moving to this cell or to this cell. And of course, in this particular case, this would actually be preferred, because this is taking me closer to the direction in which my goal is. And from there, I'll actually be reaching my goal. Okay. So this is how my search will actually be directed if I have the domain knowledge. Okay. But then the question will be, if I just erase this, my path in this particular case would be, okay, so this will be my paths. This will be the path. Given that my goal is in this direction, right? So this type of a search would primarily what will be calling it an informed search strategy, right? So this is an informed search strategy, and you can very easily see the difference between the two, right? And the mere purpose of studying this AI search strategy, especially in these types of problems, is to actually develop or to study these strategies which can incorporate domain knowledge. Okay. Now, what is this information? This information will be called a heuristic. So the information that my goal is in this direction, this is what we'll call a heuristic. So our search should incorporate this heuristic in it. And A star, and there is another search strategy which we call as best first search, best first search. these search strategies incorporate the heuristics in them. Okay, and the other one is A star. And we'll see in our next session how to implement. Right?
Excuse me, what's the name of the first one? A star and what? Best.
Okay, the first one is best first. I'll just write it in the chat. Best first. Right?